All right, so what conclusion do you draw?
The magnetic field can cause a charge in the other wire, or a current in the other wire.
But then how do you explain that the needle went back to zero?
Because it's a very brief current.
So what is actually causing the current? You're close. Someone else chime in with the answer? No, no sparks.
The onset of the magnetic field, like when it enters it,
All right,
or exits it,
sorry?
or exits it.
Okay. When we say onset, let's use more formal terminology. I guess not a whole lot more formal. Change. However, you play around with it a little bit more. So you got this hooked up to the switch. You have this wire, and you decide to play around with this, and so now you make this incredibly skinny. You got the ammeter attached to it. You make the connection. The needle doesn't quite twitch as far. It got twitched farther here than it did here. The same magnetic field is produced, but not as much current generated. What then? What's the difference between these two scenarios?
The shape of the wire.
Size.
Okay, pardon?
The length.
I mean, the length of the wire is however far around. The length, it's the same wire, so the length is the same.
The area inside that it's generating.
Okay. So if I hooked up, so we can do a third experiment. We get two of these, we double our battery power. And if I double the battery power, make the connection, I get twice of what I had over here. So therefore, the current generated here depends on what two things?
The battery in the area.
So,
The current in the area. Or
except, all right, area, yes, and
Field, magnetic field.
magnetic field. So is there some property that involves both magnetic field and area?
Yes.
Or I could have formed that as a different question of what is that property, that quantity which involves magnetic field and area?
The magnetic flux.
Yes. So what Faraday concluded was that the current that's induced in here depends upon the change in the magnetic flux. Because as soon as you make it, you suddenly have this flux that's created. It goes from 0 to something, and then it gets that steady level, because basically they had DC power back then. So you now have a steady current flowing through here, and you have a steady flux through here, so there's no current induced on this side, because you need a change in the flux. Change in the magnetic flux to induce a current. And then when you disconnect, you're going from something to nothing, again, you have a change again. Yes. Now, if I have a current flowing through a wire, let's flash back to chapter 20. What's necessary? Oh, actually, we can go back even farther. What's necessary in order to create a charge to flow? How do I have a current in general? Let's think back to the basics.
Moving electrons.
What causes the electrons to move? You have 4 different ways of explaining this. Pardon?
Attraction and repulsion.
There's one.
Change of potential energy.
So anywhere where it's going to reduce potential energy because we're going to gain kinetic. There's 2.
Yeah.
That's 3. And the one I wanted is,
Electric potential energy.
Dana, you should do it.
Electric potential then.
There we go. Electric potential. More specifically, a change in electric potential, a voltage. You need a voltage. If we're talking about current, generally you talk in terms of voltage. So Faraday concluded that the voltage, and I'll explain that symbol in just a second, is definitely related to the change in the magnetic flux with respect to time. Now, Faraday figures this out, I think this is the 1830s sometimes. Meanwhile, in Russia, a guy named Lenz actually puts the math to it. Faraday has the concept, Lenz does the math, and there's this minus sign that pops into it. And generally they talk about, hey, that's what Faraday did, and then Lenz comes along with a minus sign, and the more I read, the more I realized that this basically, Lenz came up with the math here. But the minus sign is critical. This is the no free energy. And I'll explain that in just a second. All right, so this right here, this is an epsilon. It is not an E, it is an epsilon. This stands for EMF. And for what does EMF stand? What is EMF? What is this a short for?
Energy something field.
No,
Electromagnetic field.
no. It is so incredibly simple that you are missing the obvious.
Electron meters farad.
Way too complicated. Way too complicated.
It doesn't stand for anything.
It stands for,
Electromotive
force?
no, but that's where it originated from, but that's not what it stands for now.
Does F stand for force?
No. EMF at this point stands for,
Eat my falafel.
how'd you know? EMF stands for EMF.
Cool.
Amazing.
Originally, it stood for,
Electromotive force?
yes. But the problem is, it's not a force. And this is why, even though they originally was thinking it was a force causing electrons to move, and then they realized, oh, it's not a force, it's actually a voltage. So it does stand for EMF now. Some textbooks will still say electromotive force, some will, I mean, historically, that's where it comes from.
Why don't they change these things?
How do they change these
So
things?
like, why don't they? These things that they know are incorrect. Like, yeah, they took Pluto out repeatedly because they thought that was wrong.
Because those astronomy people are just flakes. I have no idea what it takes to do the, I guess, in general, the paradigm shift. I mean, at what point is there enough groundswell? You know, you get physicists that are going, yeah, it works, so,
Preferably before they write the textbooks, probably.
yeah. Trying to think of, in terms of physics textbooks, there's Halliday and Resnick is probably one of the more famous ones. They probably had a chance to change it if they wanted to, but they chose not to. All right, so what is EMF? First off, it's basically an ideal voltage. And when I say ideal voltage, if I have a battery here, I've got a bunch of positive ions on one side and negative ions on the other side. I've got some barrier preventing them from going through, and then I have two leads. I got a positive lead and a negative lead. If I connect something to it, I will get current flow. Batteries themselves have their own internal resistance. Now, I have pretty much ignored that. There's a problem in chapter 21 where they have the battery here, followed by a tiny little resistor, and then they have the wire going on. This technically is the internal resistance of the battery. I just lump that in with any other resistance, but the EMF would be the voltage without that internal resistance, and then the internal resistance is what differentiates EMF from the voltage of a battery. So it's sort of an ideal voltage. I will use EMF and voltage of a battery almost interchangeably. The minus sign. When I create, so I got my battery here, squared off, I got my switch, and over here I've got another wire. I make the connection, I create a magnetic field. The magnetic field that I'm creating here, so the current flows this way and then down that way. This is going to be the dominant magnetic field is coming from this wire because it's the closest. It is going, current's going down at that point, so the magnetic field is coming out of the page here. We've established that it's going to induce a current, but the question is, which way will the current be induced? Is the current going to go clockwise or counterclockwise in the second wire? Let's pretend it goes counterclockwise. If it goes counterclockwise, what do we know about the magnetic field produced by this wire? If induced current is counterclockwise, what about its apostrophe there, magnetic field?
Well, along the right side, it'll be going out of the board.
Over here?
Yeah. Well, along the inside.
Coming out of the board over here.
Yeah.
All right, so it will produce, what about from top?
Also inside.
What about over here?
Also inside.
What about down here?
Also inside.
So what would happen if it's going clockwise, or sorry, counterclockwise, what's happening to my magnetic flux in the middle?
It's increasing.
Yes. Which would cause what to happen?
An explosion.
We have a magnetic field here from this wire over here. If this current went counterclockwise, it would increase the magnetic field in the middle, which thereby increases the magnetic flux in the middle.
Which continues the current.
And then what would happen?
An explosion.
Eventually. Something terrible would happen. Because basically, if it went counterclockwise, it would create a current that helped make the magnetic flux in the middle stronger. And by making it stronger, it's going to induce more current, which is going to make it even stronger, which induces more current, which makes it even stronger, induces more current, and so on. And suddenly you have a runaway current here. This thing would start to glow at some point.
And boom.
Quite possibly. Or just melt things, or shoot off radiation. Who knows what's going to happen.
And no one thinks to cut the wire.
Well, at that point, it's too late. Because you have a bunch of scientists in the 1830s going, hey, what's going to happen? Is this a salt? Let's lick it. Wow, this thing's really cool. It glows. Let's pick it up and look at it. You know, I understand they didn't know any better. However, it seems to violate the safety rules. All right. So if it went counterclockwise, we basically have a runaway current. Therefore, it doesn't. It doesn't flow counterclockwise. Therefore, it flows clockwise. What that negative sign is representing is the fact that the induced current is always going to be in the direction in order to try to reduce the change in the flux. So if this is making the flux get bigger in here, this is going to create a current which is going to try to counter that. When you shut it off, So when you open up the switch, suddenly you go from magnetic flux to nothing, the current is gonna flip directions in order to try to boost up the magnetic field in the middle. It's always gonna be it's always trying to, it opposes the change in the magnetic flux. So induced current creates magnetic field, which opposes change in the magnetic flux, not a vector, change in the magnetic flux. I find it easiest to just think through the direction of the current instead of trying to actually bring that negative sign into the problem. But there is one derivation that we will do later where we will take advantage of the negative sign there. Questions?
Would that be kind of the same thing with electric flux, or would it have a different volume?
Different ballgame.
Okay.
A change in electric flux will actually pop up again, but a little bit differently. So, if I have basically a bent rail here, I guess the bent rail will wait. Wait a spoil.
That lasts like 3 hours.
This just lasts 3 hours a day.
It'd be a dream come true.